everybody, and welcome to our next YouTube lesson or refresher all on gas laws. So back before COVID hit, we actually did, I believe, finish the gas laws unit. So all of that was done. We learned Boyle's law, Charles's law, Gay-Lussac's law, the ideal gas law. We learned stoichiometry, kinetic molecular theory, real gases versus ideal gases. And all of this is something that's also on your AP exam. So we're just going to go through a very brief overview of the different gas laws and the kinetic molecular theory, because there are about 3 subtopics within Unit 3 that deals with stuff we did in Chem 2. Hence, I already taught this in detail then, so I'm just going to review it now, and you'll have a quiz on it just like you normally would. So let's go ahead and talk about the gas laws. Before we get started, though, we want to talk a little bit about the kinetic molecular theory of gases, and we're going to go in a little bit more detail, especially with one of the postulates than we did in Chem 2, because that's something that you're going to see a lot of in the questions. As I was going through the questions for Unit 3 on College Board, I noticed a lot relating to one of these postulates, so I found an activity for us to do with that. Anyway, kinetic molecular theory of gases basically helps to describe gases and why they behave the way that they do. So states that particles of matter are always in motion, and we can use the kinetic molecular theory to explain the properties of gases. So why do gases behave the way that they do? Why are gases compressible? Why are gases fluid? This kinetic molecular theory and these 5 postulates helps us to describe gases much better. And like I said, we did this in a little bit of detail in Chem 1, and it's basically the same thing. But like I said, the last postulate, we're going to go in a little bit more depth in class. First postulate says that gases consist of large numbers of tiny particles that are very far apart relative to their size. I actually just saw a question recently for College Board, and it wanted you to draw the separation of particles for a solid, a liquid, and a gas. Notice how much farther apart the gas particles are. So the particles themselves are very, very small, but the spaces between the particles are very big. I don't know why, but this number is really sticking out in my brain. I believe I read somewhere that the space between the particles are about 4,000 times the width of the particles themselves. So the space between them is much higher than they would be for solids and liquids. So gases are very far apart. Notice that solids and liquids, there's still a little bit of space between them because it depends on the atomic radii of the atoms. Solids only vibrate back and forth. Your liquids vibrate and translate, but they're still relatively close together. But your gases are super duper far apart. So again, that number 4,000, I must have read that somewhere in a textbook years ago, but the space between the particles is about 4,000 times the size of the particles themselves, which I always thought was interesting. So as I go up, of course, temperature is increasing. So in order to get a gas, we have to increase the temperature, because an increase in temperature, or what temperature is basically how much kinetic energy the particles have, how much energy they have. So when you increase the temperature, your gases, they vibrate, they translate, which means they could slide past each other, and they also rotate. So they have the most amount of molecular motions: vibrate, translate, and they rotate. Because they have all of that energy, they're very spread apart. Like I said, 4,000 times the size of the particles themselves. So notice here, molecular interactions is actually the lowest at gas particles. What does that mean? That means these gas particles really are not going to touch each other very, very often. So like this particle is not going to collide with any other molecules very readily, or any other particles. Whereas solids, it's surrounded by other particles. So that's what molecular interactions means. These are interacting the most because they're always touching each other. These guys might collide every now and then, but for the most part, they're not going to collide nearly as often. That's the first postulate. Second postulate says that collisions between gas particles and between particles in container walls are elastic. So elastic means that there's no net loss of energy. Okay, so they could collide, and they could collide at different velocities. One could be going really, really fast, and one could be going a little bit slower. They collide, and the net that they separate after the collision is equal to the energy they came in with. There is no net loss of energy. That's what elastic means. So I have this demonstration here that I'll show you. And here it is. So if you look at these red ones here, sometimes they're going very slow, sometimes they're going very fast. So, and it's kind of hard to see with like, you have to really look at one, but within this system, this is a purely elastic system. And that's because there's no net loss of energy. Like I said, one could be going really fast and one could be going really slow. They hit each other, one could transfer energy to the other. Therefore, that's going to go slow, making the other one go faster. But there's no net loss of energy. You might remember me in Chem 2 running back and forth between the walls, right? So you would essentially go forever if it was a truly elastic collision. The third postulate says that gas particles are in constant, rapid, and random motion, and therefore they possess kinetic energy. So they're constantly moving. Gas particles are never going to be just stagnant. They're going to be moving in some way, shape, or form. Normally, they will move in straight lines. We call that an ideal gas. If it doesn't move in straight lines, then that's something else that we're going to talk about in just a few minutes. But gas particles are always moving, and they therefore possess kinetic energy. Fourth postulate says that there are no forces of attraction or repulsion between gas particles. So think of it like if you're playing pool. When you hit the cue ball into this, I don't remember what that's called. You hit the cue ball and it hits all the other balls and they all spread apart from one another. Sometimes they hit each other, they spread apart. They're not attracted or repelled from one another. They just are, right? They just go wherever they feel like going in the moment, not because someone else is there or not there. They just exist. And that's how gas particles are too. They're not attracted and they're not repelled from anything. They just are. And sometimes they happen to collide and sometimes they don't. This last postulate is the one that we're going to actually get a little bit more in depth with, not today, but I have an activity for us to do. And the fifth postulate says that the average kinetic energy is the same for all gases at a given temperature, regardless of the identity of the gas. So we're starting to bring molar mass into this a little bit. Despite the molar mass of a gas, they will have the same kinetic energy at a certain temperature. Okay, so helium gas and carbon dioxide gas will have the same amount of kinetic energy at 300 Kelvin. However, the velocities that they move might be a little bit different, which is interesting. But again, I digress. This is something we're going to do in class. Kinetic energy is proportional to the Kelvin temperature of the gas. So we're going to look at a graph like this. This is called a Maxwell-Boltzmann distribution. And what you'll notice is that your cold gases, or gases at a much lower temperature, they're usually going to possess, of course my mouse isn't moving now. Oops, let's see. They're going to be on this first blue one, but notice that it's a much more narrow curve, whereas your hot gases are much more of a rounded curve. The area under the curve is the same for each of them. So this is getting into like calculus stuff, which we're not going to get into, but you can relate it to that since a lot of you are in AP calculus. So the speed that the particles move is different, but the average kinetic energy is the same because kinetic energy is the area under the curve. Again, we're going to talk more about this in class at another time. There's two different types of gases. Gases should follow all 5 postulates of the kinetic molecular theory. And when it does, we call that an ideal gas, right? Ideal gases will follow all the postulates of the kinetic molecular theory of gases. However, a lot of gases don't follow all 5 postulates of the kinetic molecular theory. And we call those types of gases real gases. Real gases do not behave according to those 5 postulates. So I always use this as an example. You have your ideal significant other. Your ideal significant other has to have all these qualities, right? This. And then you find somebody and they might not have all of those qualities, right? You have your ideal significant other. This is what I want. But then you have your real, like you got to level with yourself. Like, okay, they're not going to have all of the qualities that I'm looking for. It's going to be very difficult to have that. Gases are the same way. Ideal gases will follow all of those 5 postulates, but they're not always going to follow all 5 postulates. Most gases will behave more real in a sense. Some gases have the ability to behave very ideally, and we'll talk about those 2 scenarios in which you can have an ideal gas and what kind of forces an ideal gas to become a real gas. So what are those scenarios? How can a gas behave more ideal, and how can a gas behave more real? Let's talk about temperature first. So in this case, I have a gas at 2 temperatures. So I have a much lower temperature here on the left-hand side, and I have a much higher temperature on the right-hand side. So if we were to think about which one of these gases follows all the postulates of the kinetic molecular theory, hopefully you would say the one on the right follows all of those postulates. Let's look at the one on the left. So we have a very, very low temperature. What does that start to do? What can the gas particles start to do at a very low temperature? Well, first of all, that first postulate's thrown out the window. Particles are far apart relative to their size. Because if I look, I mean, some of the particles are super, super close. So they're very close to one another. First postulate's gone. Also at a low temperature, if they're very close to one another, especially if we have polar molecules, those molecules can attract or repel each other, right? Dipole-dipole intermolecular forces of attraction. If they're super close, they'll start to attract each other. So at very low temperatures, you'll find that gases behave more real than they do ideal. So at low temperatures, gases are going to behave more real because they're not far apart relative to their size. And therefore, because they're, the pressure or the volume that they take up is so much lower, they could start to attract or repel one another. So high temperature is when you start to have more of an ideal gas. So low temperature is when you can have a real gas. That's why that one's circled. Let's talk about pressure as well. So at which pressure will you start to have more of a real gas? Well, again, think about those 5 postulates and even just what we talked about on the last slide. So here I have a gas at a very low pressure on the left, and on the right, I have a gas that's at a very high pressure. The one that's at a high pressure, again, the particles are very close relative to their size. Because of that, they could start to attract or repel one another. The scenario on the right, therefore, high pressure is going to lead to a gas behaving more real than ideal. So at a high pressure, that also leads us to have a gas that behaves more real, is because the particles are not far apart relative to their size, and therefore they could start to attract or repel. I mean, Coulomb's law, they're closer to one another, they have a chance to attract one another much more readily than they would if they were far apart. So, just to go over this, gases that are likely to behave ideal are gases at high temperature, because the higher the temperature they have, the more kinetic energy they have, the farther apart they want to be from one another. And at low pressure, and also small nonpolar gas molecules. For example, helium, neon, hydrogen, even oxygen, anything that's very small and nonpolar will generally behave more ideal. It will follow all 5 postulates very, very easily. As opposed to gases that behave more real, they're not going to follow all 5 of those postulates. Gases at a low temperature and a high pressure, because in both scenarios, the distance between the particles is very small, and as a result, they could start to attract or repel one another. Also, if you have very large or polar, especially polar gas molecules, they have the ability to behave more real. If I look at these 2 examples, so ammonia and water, both of those have the ability to hydrogen bond to one another, which is a very strong intermolecular force. Even though those particles themselves are pretty small, because they're very, very polar, they could attract or repel, especially if they're not at a very high pressure, or if they are at a very high pressure, they could start to attract or repel. So they're more likely to behave more real. They will deviate from ideality, is what we say. So again, deviate from ideality. If you're deviating, you're kind of going off the course. So if you're deviating from ideal gas behavior, you're behaving more real. You're not following all of those 5 postulates. This is one big section of gas laws for College Board, is it was the difference between ideal gases versus real gases. So I would definitely know this, and especially how to explain that. Let's talk about pressure. So of course, gases are compressible, and as a result, we can increase the pressure of gases. Pressure is just the force per unit area on a surface. So if you put air in your tires, you increase the pressure of your tires, there's more force per unit area inside the tires. And there's a lot of different units of pressure. So you'll see on here, there's a few of them. There's the Pascal, millimeters of mercury, or torr is very common. Atmospheres is also a common one. PSI, not so much. I don't know if this is on your, I gave you like a College Board thing in the beginning of the year that had some conversions on it. I'm not sure if those are in there, but I would just know, and you can make a note of this, that 1 atmosphere is equal to 760 millimeters of mercury, which is equal to 760 torr. I would definitely be familiar with that conversion as we progress through gas laws. And of course, before we get into the gas laws, we have to be able to recognize STP. STP is a very important part of gas laws. What does that mean? If I have a gas at STP, that stands for standard temperature and pressure. And we use STP as a means of comparison between scientists. If I'm doing a reaction here, or if we're doing one at Wallenpaupack High School, the temperature of the school is going to be different from maybe other schools. And we're at not a really high elevation, but we're at an elevation, right? We're going to be a little bit higher than sea level. So atmospheric pressure is a little bit different. If we were comparing our data to somewhere in Hawaii, where it's going to be much warmer, and the pressure there at sea level is going to also be much higher, not much higher, a little bit higher, then we can't really compare them because our temperature and pressure affects gases, and we need a means of comparison between them. So what scientists have determined is they've come up with just a standard. So STP, standard temperature and pressure. And a gas at STP is always at 0 degrees Celsius or 273 Kelvin. If you forgot how to convert Celsius to Kelvin, all you need to do is just add 273. So standard temperature is 0 degrees Celsius or 273 Kelvin, and standard pressure is 1 atmosphere. So if a question is asking you how many liters of gas can be produced at STP, that's at 273 Kelvin and 1 atmosphere. Again, it's just a means of comparison, because if we did an experiment in our high school, we would obtain some volume of gas, but somebody in Hawaii doing the same experiment might contain a different volume of gas based on the temperature and pressure of their location. So granted, it might not be a huge difference, but when you're studying gases, you want to be as accurate and precise as possible. So we have this means of comparison. Let's talk about the gas laws. So these are mathematical relationships between volume, temperature, and pressure of gases. We'll get into the ideal gas law as well, and we can relate moles to that. Now I'm just going to fly through these quickly because these are not a very difficult concept to grasp. Plus, we did them in Chem too. First is Boyle's law. Boyle's law is a pressure-volume relationship, and your pressure varies inversely with the applied pressure at a constant temperature. I always remember Boyle is independent of temperature, because if you have a pimple on your face, normally you want to increase the pressure in order to decrease the volume, right? It's gross, but it makes sense. So Boyle's law is a pressure-volume relationship at a constant temperature. When you're doing that, the temperature of the atmosphere in your skin doesn't change, so temperature is constant. And your equation looks like this. P1V1 equals P2V2. So the pressure and volume of the first system is equal to the pressure and volume of the second system. So here we go. If I have some gas in this vessel on the left-hand side, it's exerting some pressure at some volume. If I were to take that and to compress that volume, so if I were to take it and make it take up half the space, the pressure would go up. And that's because you're forcing those gas particles together. The force per unit area is going to go up. There's a lot more collisions within the gas particles themselves, but the particles are also colliding with container walls much faster. So when volume goes down, the pressure is going to go up. And the relationship between those is actually a hyperbolic relationship. I don't know too much about this. I do know that there's two asymptotes, because pressure can never technically be at zero, because you can have 0 atmospheres, and you also can never have 0 liters. Doesn't happen that way. So it'll never actually approach 0, which is why we have this hyperbolic scale. Just know that when a volume goes up, the pressure is going to go down. It's not directly proportional like the next two gases are. So it varies inversely. So our graph is actually going to look a little bit different for Boyle's law and Charles's law. It's not going to be hyperbolic. The next law is Charles's law. And Charles's law is a volume temperature relationship. So when the temperature goes up for a gas, the volume is also going to go up. It's directly proportional to the absolute temperature. So Charles's law says that the volume of gas occupied by any sample of gas at constant pressure is directly proportional to the absolute temperature. So V1 over T1 equals V2 over T2. So when the temperature of a gas increases, the volume of the gas is also going to increase. When you increase the temperature, the amount of energy the particles have increases, their kinetic energy increases, and therefore they want to take up more space. And this is directly proportional. So you should find that you don't have to use a calculator to do this. Let's say I have a temperature of 200 Kelvin and the volume is 1, right? So if I have 1 liter at 200 Kelvin and I want to know what would the volume be at 400 Kelvin, it really should be 2 liters, right? Because it's directly proportional to one another. You don't always have to plug things into the calculator to do these types of equations. I'm going to give you some examples like that in class because, of course, you can't use a calculator on the multiple choice section of the exam. So we should get comfortable with doing some of these without them, and they're not going to be very difficult, but just to get us familiar with that. Here's an example of Charles's law. So you have some liquid nitrogen here, and you have some balloons that are filled up, and you take those particular balloons, put them in the liquid nitrogen. When the temperature goes down, the volume is also going to go down. And that's because the kinetic energy of those particles is significantly decreasing. When you take them out of liquid nitrogen, like that third picture is showing, they'll actually blow back up, because when temperature increases, your kinetic energy of the particles increases, thus increasing the volume. Pressure is constant here, and pressure is constant because the pressure of the atmosphere is not changing. So with these, for example, this doesn't have pressure in it, pressure is constant. Boyle's law doesn't have temperature, temperature is constant. Here's a graph. This is a linear graph that represents Charles's law. And you can technically have this, I believe, because you can reach a temperature of 0, that is absolute 0, 0 Kelvin, where all molecular motion ceases. I would have to do a little bit of research myself on the volume section, but I do know that this is definitely a linear relationship. They are directly proportional to one another. When temperature goes up, your volume is going to go up in the same ratio. The last law is Gay-Lussac's law. Well, not the last law, but the last basic law, I should say. And this is a pressure-temperature relationship where volume is constant. So it looks very similar to Charles's law, except instead of volume, there's pressure. And again, it is directly proportional, so you should be able to do equations with this also very, very easily. Not very many examples to kind of go along with this, but I did think of this one. So if you leave a can of soda in the car, it will explode if it's very, very hot out. And the reason for that is because the volume of the can is constant, right? The volume of the can isn't changing. So what is changing, however, as the temperature of the gas is increasing, if it's in the hot car, the pressure that those gas particles, the carbon dioxide bubbles inside of the soda can, they're going to increase pressure, but the volume of the can stays the same. So eventually, when the temperature is brought up enough, the can will explode because it can't withstand that volume anymore. So when pressure goes up, temperature also goes up proportionally. And it's actually the same exact graph for Charles's law. So, and again, that's because you can reach absolute 0, 0 degrees, or 0 Kelvin. Again, like I said, I have to learn a little bit more about this myself. I don't think that's on your test anyway. So, but you might have to know just like general representations, like knowing that it is a linear relationship where volume and temperature go up proportionally. You might just have to be able to recognize that. And then, of course, we can take all of those and combine them into one. And we literally call that the combined gas law. So it expresses the relationship between pressure, volume, and temperature. So P1V1 over T1 equals P2V2 over T2. Not too many applications of the combined gas law, except if you are correcting something to STP. So let's say, and we are going to do this in one of the labs in class, but if we collected 2 milliliters of gas at our conditions, we want to know what volume of gas would you have collected at STP. You can correct it using the combined gas law. Another gas law is Dalton's law of partial pressures, which is always everybody's favorite. And Dalton's law of partial pressures says the total pressure of a mixture of gases is equal to the sum of the individual pressures of all the component gases. For example, there's your equation. Oh, I thought there was going to be a picture here. So the total pressure of the mixture of gases, so atmospheric pressure, let's say the pressure right now that is surrounded by me, and if you look on your phone, actually you can look up atmospheric pressure. Let's see. That's Hawley. So Scranton, the pressure is 30.34 inches of mercury. okay? That's the total pressure of all the gases that are around me. That pressure is equal to the individual pressures of all the component gases that make it up. So in the air, it's 70% nitrogen. That nitrogen is exerting some pressure in this atmosphere of gases, plus the partial pressure of oxygen gas, which is also around us, plus the partial pressure of carbon dioxide, of water vapor, of helium, of whatever gases are surrounding us. All the sum of all the component gases that are in air makes up the atmospheric pressure, which in this case is 30.34 atmospheres. Here's the picture that I thought was coming up next. So here, notice all of these are at the same temperature and the same volume. So in A, I have 2.9 atmospheres of hydrogen gas. In B, I have 7.2 atmospheres of helium gas. For some reason, we're adding them together. And that's what C is showing. The total pressure in the same volume and temperature is just the sum of both of those gases. So the 2.9 atmospheres that hydrogen exerts plus the 7.2 atmospheres that helium exerts equals 10.1 atmospheres. That's going to be the pressure of the system when those two gases are added together at the same volume and temperature. That's Dalton's law of partial pressures. The sum of all the component gases, their pressures, is equal to the pressure of the whole system. And there's a really good application for this, and this is gases collected by water displacement. And again, we're going to do at least one lab with this in class. When you're collecting a gas over water, first of all, it's very hard to collect gases in general in experiments, because how do you collect the gas, right? Where do you collect the gas into? And one way you can do that is by water displacement. So you have some reaction in this flask, and it looks like it might be hydrochloric acid and maybe some metal, so maybe calcium or something. It's producing some amount of gas, and that gas is going through that tube. I wish the mouse was working. I don't know why it's not. Now I got the mouse to work. So this gas is being produced. It's going through this tube, and you can collect the gas above water. It makes it easy to do that, and then you can measure the amount of gas that's produced. This doesn't really look like a very good measuring device because I don't see any graduations on it. So, however, the pressure in here is equal to the atmosphere, right? And you can find the pressure of just the hydrogen gas that's produced because it's the pressure of the atmosphere. However, not only do you have the hydrogen gas in here, your water is evaporating just a little bit, and it depends on the temperature of the water. Therefore, you have to take that into consideration, because water is always evaporating unless it's at 0 degrees Celsius. It's exerting some pressure on the environment. So to find the partial pressure of just the hydrogen in here, because again, there's water molecules in there because I'm collecting this over water and they're evaporating, the atmospheric pressure, so that's PATM, is equal to the partial pressure of the gas, which is hydrogen, plus the partial pressure of water at that temperature, okay? Because the water is evaporating just a little bit, and we have to account for that because it's and we can look up what is the vapor pressure of water at different temperatures by using a chart. So this is our water vapor pressure chart. This is the one I normally give everybody. So this tells me the pressure of water in millimeters of mercury and in kilopascals at a whole bunch of different temperatures. And you'll notice that as temperature is increasing, the partial pressure of water actually increases. So at 5 degrees Celsius, let's say, water will exert a pressure of 6.5 millimeters of mercury on the environment. it's not very high at all. That's because not a lot of water molecules are evaporating. However, as the temperature is increasing, the pressure that water exerts on the environment is going to go up. Again, that's because it's starting to evaporate. And when more water molecules are evaporating, they're in the gaseous state in that system, they exert a higher pressure in the system. So, like we said, you have to account for that. You'll notice that at 100 degrees, the partial pressure of water is actually equal to 1 atmosphere. And that's why water starts to boil, is because when the pressure that the water exists on the atmosphere is equal to the atmosphere itself, that's when water starts to boil. So that's a fun little fact of information. I'm not sure if we get into that in this course. I might add that more into Chem 2. But when vapor pressure equals the atmosphere or the pressure of the environment, that's when something starts to boil. Ideal gas law, super crucial. The ideal gas law is a relationship between pressure, volume, number of moles, and temperature. So if I had a gas at some volume, some pressure, and some temperature, how many moles of the gas would you have? PV equals nRT, where P, of course, is pressure, V is volume, N is the number of moles, R is a constant, and R is 0.08206 liters atmospheres per mole Kelvin, and T is temperature. So unlike with Boyle's law, Charles's law, Gay-Lussac's law, and Dalton's law, and the combined gas law, I think I said them all, it really doesn't matter what unit you put your pressure and volume in. It only matters that your temperature is in units of Kelvin. Here you do have to have pressure and volume in certain units. Pressure must always be in units of atmospheres. Volume must always be in units of liters. If it's not, you do have to convert it. Temperature, like always, has to be in Kelvin, but that's nothing new. But that's what R is, your ideal gas law constant. Or that's PV equals nRT. And what we can do is we can derive other equations from the ideal gas law and solve for the density of a gas and also solve for the molar mass of a gas. And I'm actually going to pull up a whiteboard here to show you how we can derive new equations from the ideal gas law. So I want to show you how we can change PV equals nRT, and we can find the density of a gas, and we can also find the molar mass of a gas. We're actually going to solve for molar mass first. So that's what this big M is here. So this is molar mass. What we can do to start with this is we can start with using N right here, the number of moles. And if you think back to just very basic mole conversions, hopefully you remember that your number of moles is equal to the mass of a sample divided by its molar mass, capital M. So the number of moles is equal to the mass of a sample of gas divided by its molar mass. This is crucial. I think this is actually on one of the gas law sections. I'm not sure what, but moles is equal to mass divided by molar mass, which you know already, just not in this type of equation. What we're going to do is we are going to plug that in to PV equals nRT. So we'll do PV equals mass divided by the molar mass times RT. And what we're going to do to solve this for molar mass, we're just going to rearrange this equation a little bit. So PV equals little m RT over capital M, molar mass. And if you rearrange this a little bit more, you would find that the molar mass of a gas is equal to the mass of the sample times R times T divided by its pressure and volume. So you could literally rearrange the ideal gas law and solve for the molar mass of a gas. You could also just use PV equals nRT in itself and then do a couple of little side problems, but this is another way to represent the ideal gas law. This is also the ideal gas law. We're just representing it a little bit differently. What we can also do is we can solve for the density of a gas, and that's another derivation of the ideal gas law. So what I'm going to do is I'm just going to rewrite this equation that I have up here. M equals mRT over PV. And hopefully you remember that density is equal to the mass divided by the volume. D equals M over V. And if I look at this equation, I actually have density in here. I have mass divided by volume. So we are going to take that and plug in density for that M over V. So molar mass is equal to the density times RT over P. Okay, so I took out M over V and I plugged D in there. We're going to rearrange this again algebraically, just so that way we're solving for density. So M equals dRT over P. And eventually you would keep solving this. I'm going to spare you of the minute details, but the density of a sample of gas is equal to its molar mass times its pressure divided by R times T. Let's see if we can get the same color here. Probably not. Oh, pretty close. So these are two derivations of the ideal gas law. Both types of the ideal gas law, but just not the ideal gas law with PV equals nRT. You don't have to know the derivation, but I like to show the derivation because a lot of your upper level chemistry classes that you'll have in college will be all derivations. I mean, I could show you some of my lab note or some of my notebooks. They don't even look like chemistry. It looks just like a math notebook with calculus, and I'm not good at calculus. Algebra I can do, but not, I never had a good calculus teacher, but that's a whole thing in itself. So again, these are just two other derivations. That's where I'm going to stop this video. If you have any questions, let me know. I will put some worksheet together with some practice problems. But again, this is all a review from Chem 2. And even with COVID, you guys were here for all of that. So I'm going to log off and email me if you have any questions. Bye.